Hello. In this lecture, we are going to talk about and give some examples about graphs. Graphs are, as you well know, visual representation of mathematical functions usually, or statistical data, for example. Usually, the graphs are showing us the relation between two variables. They can be dependent, or, as we will see in the end of the lecture, they may not be dependent. But what is the relation between these two variables? Variables are numbers, usually measured numbers, measurements, I mean. And when you measure one variable, what is the value the other variable takes? The graphs show us this. There are two basic types of two-dimensional graphs. One is a linear graph. In a linear graph, the y and x axes, if 2 points on these axes has a similar or equal separation between them, it means that the difference between values, the difference of the values of these points are always equal. Here the scales are different. So for the y-axis and the x-axis, the same displacement does not correspond to the same difference in values. However, for a single axis, it's consistent. You have to be careful about the units and the scaling of the axes. They may not be the same. However, for a linear graph, the distances always, for the same axis, the same distance always corresponds to same difference in the value of that parameter. Another type of logarithm is a semi-logarithmic graph, or a log-log graph. We show here a semi-logarithmic graph. Semi-logarithmic graph means that one of the axes, it can be the y-axis or the x-axis, usually it's the y-axis, but it doesn't have to be the y-axis, is in the logarithmic scale. So here the same amount of shift or displacement on the logarithmic axis do not correspond to a similar change in the value of that parameter. You can see here in the left hand side in the linear graph the lines in horizontal lines that are drawn in different colors has different values. It's 10 for the red for the 10, blue, light blue for 100, and orange for the 1000. So as you can see, their separation is different. However, when you plot the same points on the semi-logarithmic graph, you'll see that they have equal separation. Because when you take the logarithm of 10, it's 1, and 100, 2, and 1000 is 3. So the logarithm of those values is separated equally. Here, I did not plot, or I did not put the logarithmic values, but instead not the logarithms, but the values themselves. But they are placed on the axes where the logarithms should go. So you can either put the logarithms there, or in some cases people put not the logarithms but the values themselves, but they place them where the logarithms of them should be. So this is semi-logarithmic graph. What's the use of using semi-logarithmic graphs or logarithmic graphs? There are several uses. this representation is actually helpful. That's why it's used. It's not just to make things fancy. For example, if you have an exponential function, here you can see the relation between the x and y values. And if you want to, for example, if you make a measurement, an x and y pairs, or measurements of x and y pairs, and their relation is exponential, say. There is a curious property of exponential function. When you take the logarithm, the natural logarithm of both sides, you see that the new y, say that's y prime, let's say, equals to a times x. So this graph, if you plot the x versus the logarithm of y, and if the relation between x and y is exponential, when you plot the x value against the not y but the logarithm of y, you end up with a line. It becomes linear, and the slope of this line is the exponential factor a. So if you're dealing with exponential functions like the growth of number of cases in an epidemic, for example, the early phases of an epidemic, then if you use instead of a linear graph, if you use a semi-logarithmic graph, you can see that if it's the growth is exponential, or there is a drift from, or a shift from exponential to more linear behavior easily. And also you can easily calculate the factor a by looking at a linear graph without having fancy mathematics, doing fancy calculations. It's the same relation, by the way, but instead of giving the y values, we plot the logarithm of the y values. So it becomes linear. The difference between the adjacent points getting bigger and bigger in the exponential function, however, the distance between adjacent points in a logarithmic, semi-logarithmic graph on the y-axis gets larger and larger, even though this distance on the graph between these adjacent points is the same. They represent larger and larger differences in terms of units. So this linearizes the graph. This is just an example for the use where we use logarithmic graphs. Logarithmic graphs are used very often, so you have to understand the logic behind them. They do not change the function. They only represent the function in just a different way, the same function. However, this different representation has some advantages. But be careful, as I said, this linearization also makes things easier to calculate the a, the parameter a. However, the slope is the parameter a, the exponential factor. However, you have to be careful that, first of all, it's only the case if you take the natural logarithm of it. Here we take the logarithm to the base 10. So we have to do a conversion. And secondly, if you divide the y to the x here, you won't get the a, naturally, because the numbers are not the logarithms. The numbers are the numbers. The placement is logarithmic. So you have to divide these numbers to these y values to the x to get the real factor, the a. So you have to be careful about these things when you're doing that calculation, trying to find the a. Okay. Graphs are usually displaying the relation between two variables. There can be three variables also, but three-dimensional graphs. Usually the graphs are two-dimensional and show relation between two variables. However, these two variables one of those variables does not have to be time, always. There is a tendency to show the independent variable on the x-axis and the variable that depends on it on the y-axis, but it's not a rule, by the way, it's just a convention. So don't be fooled. Don't just assume that the x value is time, or don't just assume that the x value or the x-axis represents an independent variable, or do not assume that the x-axis represents time. It's a very common mistake. It's a very easy mistake to make. For example, here you see a binding reaction, and the binding reaction is evolving with time, and the graph, the red line, shows the concentration of the A and AB complex. It starts with 0 AB complex, because there you mix together the free A and B substances. Then the complex starts to occur, its concentration increases, and then it comes to a certain point and stops increasing. I mean, it reaches an equilibrium point, it's called. So if you start with a certain with a fixed amount of B, fixed concentration of B, but if you change the concentration of A, the starting concentration of A, then you'll end up with different points or different graphs and different endpoints. The A01, A02, A03, A04 represents the starting concentration of A. A0 means the starting concentration. And these lines represent the change in concentration of the AB complex throughout time. Okay, so what we can plot is these equilibrium values, the endpoints of each line, versus the starting A concentration or A0 concentration. So different A0 concentration gives us different end values. So this is the plot of it. This is an equilibrium plot. So now the x-axis is not time. The x-axis is the starting concentration of A0. And the y-axis is the endpoint, the equilibrium value of the AB complex. Okay? You can also plot not the starting concentration of A0, but then the equilibrium concentration of free A. The equilibrium concentration of free A is not 0, by the way. When binding reaction reaches equilibrium, the free A concentration is not 0. So you can also plot that versus the final equilibrium concentration. This is an example of a graph showing the interrelation between two variables. However, none of them are time. But they are interdependent. Here the A0 or the free A at the time of equilibrium is the independent variable, because that's what we change during the experiment. And the AB concentration, the concentration of the AB complex, is the dependent variable, because it changes according to the change in the A0 concentration. So when we look at another example, here there are two variables. One of them is shown in red, the other one is shown in blue. These two variables is a function of time, so we measure them as time goes by, and we make simultaneous measurements of these two variables. These two variables may have same units, may have different units. They may be interrelated, or they can be completely independent from each other. We do not know that. However, we do simultaneous measurements of these two variables. And as you can see, each time point or each measurement point has two values for it. For the blue variable, the other for the red variable. So you can plot these on a graph which has the axis of blue variable and the red variable values. So instead of plotting them against time, you plot them against each other. So here, well, how we do it, we say that at that point, 10th time point, the value of blue is represented on the x-axis, and the value at that same time point of the red variable is represented on the y-axis. So it gives us a single point representing that measurement in time. Now, as you can see, the graph in the below do not have any information about time. So, for example, we go to the 14th measurement, time point measurement. Again, we measure two numbers we measure, one for the red variable, one for the blue variable, and we plot them accordingly. And now we have another point. We do not know which point comes first, just looking at the graph below, the lower graph. You have to have it, you have to have the information, both information on the upper graph and the lower graph, and you have to match them. And also, if those variables time to time has the same value, repeating values, then which one of them represents the later ones, which one of them represents the former ones, cannot be distinguished from just looking at the graph, lower graph. However, what it gives you that what is the dependence between these blue and red variables? When you look at the time graph, it's very difficult to see something because they just move up and down randomly. They just fluctuate. They do not seem to have any pattern. They're not going up or down or anything. Just fluctuate around the same value, both of them. Is there any correlation between them? If one goes up, does the other one goes up? If the one goes down, the other one goes down. It's very difficult to tell just looking at the graph. If you have many more numbers, then it'll be even harder to see. However, if you plot them one against the other, you see that there is a clear correlation between them. It's not a linear correlation, even it's an interesting correlation because as the value of blue gets larger and larger, the red tends to increase faster and faster. Let's try to understand what's going on. As you can see, the blue value is in between these two lines. The blue changes from 0.5 between 0.5 and 1. So as you can, when you look up on the top graph, that you'll see that yes, the value of blue moves between 0.5 and 1. However, the red moves from 1 between approximately 1 and 3.5. So when you look at the red axis in the graph below, yes, it's moving between 0.5 and 3.5. However, the data on the graph below do not have any time information. When you pick up a point on that graph, you cannot tell, 2 points, let's say you pick up 2 points, you cannot tell which one comes first, which comes next. It only shows that when one goes up, the other also goes up. When one goes down, the other also goes down. A very similar type of measurement. We have a kind of different look to it. However, the variables again move in a very similar ranges. For blue, it's 0.5, between 0.5 and 1. For the red, it's between 1 and 3.5. However, when you plot these one against the other, you see that there is not much correlation between them. So these two things may not have any relation. So they just can be independent. So plotting one variable against the other actually reveals such interdependence between variables. Let's give a real example. So there are two variables measured between 6th and 10th months of 2020. These are real statistical data from the Turkish Ministry of Health. These are for Istanbul. Two variables are the daily hospitalization numbers, the number of cases hospitalized due to COVID-19 illness, and the blue data represents the reported cases of COVID-19 patients, which means that the COVID test positive number of cases each day. So for a period of time, these numbers are measured in Istanbul. As you can see, the daily number of reported cases, the blue, goes down for 40 days, then it starts to goes up, and then it picks up speed or pace after the 100th day. So 0 day is the beginning 29th of June. The data represents 120 days approximately. So when we plot daily hospitalization numbers against the daily reported cases, and we put the daily reported cases on the x-axis and the daily hospitalization numbers on the y-axis, we will end up with something like that. Again, be careful that the graph below do not tells us what's going on as time goes on. For example, it doesn't mean that the daily hospitalization is increasing by time. It can be decreasing by time. It can be first increase and then decrease by time. Anything can happen. But what this tells us that there is a relation between the daily hospitalization and daily reported cases. As the daily reported cases increase, daily hospitalizations are also increased. And their relation seems to be more or less linear. However, if we have to look a little bit closer, for example, when we look at the daily reported cases between 100 and 300, so I shaded it in pink for both graphs. You see that the that part of the graph below has larger values for the Y, daily hospitalization. But for the rest, for the daily reported cases larger than 300 up to 800, we don't see that that much high Y values, daily hospitalizations. So let's divide the graph into two. Until 40th day, the number of daily reported cases is declining, as you can see with the light blue. And then after that, it starts to increase. And you can also divide the increased part into two, because the pace after the 95th day or the 100 days, it starts to pick up pace. However, we'll just divide it into two. And we can divide the graph and or the plot below into two too. You can see that the first part is represented by light boxes, and the second part is represented by darker squares. What we see is actually, of course, here it means that in the first half, the daily reported case is going down by time. But when we look at it, not as a time sequence, but the relation between those two, the relation is steep. So as the number goes to 300 daily reported cases, the daily hospitalizations go up to 140. So almost half of the patients is hospitalized. However, when you look at the later part of the graph, here the graph goes from left to right. As time goes by, the number of cases, daily reported cases, increase. However, don't think about it, but when you look at it, for example, when the value goes to 300, daily reported cases on the x-axis goes to 300, daily hospitalizations just increase about around 60 or 70, half of what was before. So the slope of these two correlations is not the same. About one of them, the later part, has a slope almost half of the slope of the former part. So there are two things going on here. So in both cases, the number of the daily reported cases is correlated with the daily hospitalizations. But the correlation is sharper or larger for the former part of the process than compared to the later part of the process. This is real data given by the Turkish Ministry of Health. Of course, what does this mean, and what information you can deduce from this is up to you. But this graph tells you that basically, or simply, the hospitalization rate, which means that the hospitalization rate is the number of hospitalization cases divided by the daily reported cases, is different for two halves of this epidemic event. Okay, this is the end of the lecture. I try to give you some examples about unusual type of graphs, which you may not be familiar with. Of course, this is not the whole story. You have to keep these in mind, and there are other types of graphs you may encounter. So you have to understand the graphs and decipher the information locked in them by using the hints I gave you in this lecture. See you in the next lecture.